Hello and welcome to Entering Scale Models. I'm Jason, your host, and I do models and apparently electronics and educational things. This is getting crazy in here now. Let's check out what we're doing. This is going to be an overview of my book I got from Brock Lemire's. I got it off of Amazon based on his YouTube channel. I'll show you that in a minute. This is Introductions to Circuits and Logic Design with Verilog. He has two books, one with VDL, one with Verilog. I chose Verilog because it's a system I'm semi-familiar with. But he has a web YouTube channel called Digital Logic and Programming. He's a teacher at Montana State University, I believe. And he has a lot of great videos, electrical engineering and things like that. But he also wrote these two tech books that he's done videos on, embedded designs, embedded system designs, which I talked about in a previous video and went over what I learned in chapter 1. And then he also has this digital logic, logic circuits, which covers what's in this book. And it's 149 videos plus some lab videos. So if I show you the playlist here, it goes through like chapter 1, chapter 2, chapter 1 videos. Chapter 2, it's pretty long. You're learning the number system and the conversions and stuff. And you can follow along in the book, and it's fantastic because if you get stumped, he does many examples in the video. Fantastic stuff. I hope he writes another book because it is just fantastic. So, you have a reference with videos if you want to go through this book and learn these systems. I don't know. This is like a textbook. It cost a little bit like a textbook. I think it's like $75, which is expensive for a book, but it's extremely good quality. It's extremely well written. I just did a video on the embedded systems in chapter 1. I've gone through chapter 1 in this. Chapter 2 is basically the number system. It's pretty long, and then we're going to get into logic families. I'm still going through chapter 2. I'm doing chapter 2 of this one this week, and then chapter 2 of the other one next week. So it's basically a pretty big chapter, and then it has a good amount of questions you can answer at the end, and I'm writing all the answers out so I can go over with you guys as I complete a chapter. So I don't want to show a lot of what's written in the book for copyright reasons, but I'm not sponsored by this. I bought this with my own money, and it's a fantastic way to learn logic circuits and logic design, and I'm eventually going to use it to use Verilog with the Xilinx software and some Xilinx FPGAs. But I just want to go over here what I took from chapter 1, which was about the differences between an analog and a digital system. And it was pretty informative. Like, I knew analog systems, but this actually got me thinking, like, what is actually, how have we evolved from analog to digital? And some of the key points here is an electrical signal is considered analog if it's a direct function of a physical quantity. So if you have a radio, like a sine wave, and you put a sine wave input and you take a sine wave output, there's just a continuous flow. So you're measuring every single point of the sine wave and outputting that sine wave. A digital signal is a discrete representation of information. He explains this way better than I could ever explain it, but it's basically a digital signal takes bits and pieces of said sine wave and transmits it into highs and lows in a digital signal that is different points of time, different readings, and then you can extrapolate what the signal did by filling in the missing spots and basically connecting the dots. An analog system would always require an analog component. The sound coming out of an earbud is an analog signal converted from a digital signal. So your music on your phone is stored digitally, and then that is converted to an analog sound wave from an original digital signal. Now, if I get any of this information wrong, please correct me in the comments. This is how I interpreted things. Some of these may be incorrect. I just answered the questions that I thought how I learned the system. So an MP3 file is stored with a digital system. That's, that's standard because it's stored in memory. The circuitry that reads an MP3 file is digital. The signal that travels down the earphone wire, that's an analog signal because it's a continuous waveform. The voltage coming from a battery is, see, this is where I was doing, is an analog value. It is a continuous either 9 volts or 1.5 volts or 3.2 volts. Whatever your battery voltage is, it's a continuous thing, and as it dies, it slowly tapers off. So I got that as an analog signal. The voltage, oh, nope. The touch interface on an iPod is, as a digital system, reading the touch. And then I have, was asking what digital systems I use. And my digital multimeter uses a digital system to read analog values. And my trackball uses a digital system to talk to the computer. So, my analog movements of my trackball that I'm currently using uses a, takes that, continuous motion and transfers it to a digital signal, and then it through ADCs, analog to digital converters, and then digital converters to analog converters to get you the movement. I believe I'm getting that right. Not 100% sure. And then I have a little mini drill press, and to my knowledge, it uses an analog system to spin the chuck at a set speed using a speed controller. So as you turn it up, it gives it more power, and it spins it. It's not converting. It's not converting the AC. It's not chopping up the AC signal to DC and then taking different readings and then outputting it. It's a straight analog system. Also a fan, a fan, you turn it on, it spins. It takes power in and it spins. And mine runs on a USB port, and it runs it at a set speed. An analog clock would have a smooth second hand, but a digital clock would have a second hand that would pulse forward every second. So if you look at the old analog clocks, they just move, the second hand just moves real slowly. But if you had a digital clock that was completely digital and you had it outputting to a second hand, the second hand would tick like this. So that is my interpretation of how a clock would work. A digital system uses less power and can be smaller and do more things over an analog system. Analog system needs constant power to constantly output the analog system data. By a digital system takes bits and pieces at set intervals, so it doesn't need to be running 100% of the time. And then it talks about what has evolved in my time from an analog to a digital system. I talked about this in my embedded systems video. Check that out. I talked about a toaster. It's evolved from an analog system to a digital system in my lifetime. It went from just pushing down the lever to a digital system with timers, temperature readings, controlled by an embedded system. So, back when I was a kid, you had the hot coils, you push the lever down, and then it ran for a set amount of time with a little ticker timer in there, and then it popped up the toast. Now it's all fancy and, reads the temperature of the bread just to get the perfect crispness and all that stuff. An analog system that has become obsolete in my time. That was hard for me. But I would say analog radios are falling out of use in the mainstream. They're all digitally tuned now and things like that. But it's still fun as a hobby to build them, but not really practical for daily use. Normally you use a digital system. Analog radios, I mean, they're still around, but they're not as popular, and they're getting towards being obsolete. And I would say that music went from the analog days of records to CDs to digital music on your phone. But there are still people that say it sounds best on vinyl, that analog system of vinyl, and that audiophiles love that sound. So a lot of people are like, you can't, converting it to digital, you lose something in the sound quality. So, and then I would also say modern test equipment like my oscilloscope, my digital storage oscilloscope, could not have the possibilities that are available to us today back when they were analog devices. This was a big change that changed in my lifetime when I was learning electronics in high school. That was all we had was analog oscilloscopes, and they were limited on what they could do. Also, they were easier to damage because there wasn't a lot of protection built into the oscilloscope. Oscilloscopes still, if used improperly, it can be damaged. But, basically you saw a waveform on an analog scope, and that was, you really couldn't do a whole lot. It had the tube in it, and I remember using those in high school, and digital oscilloscopes I don't even think were out then. But now I have a digital storage oscilloscope, and it does so many things. It can do math. It does fantastic stuff. So I would say that is something that's changed for the better. And then we're talking about how many transistors can you slap into a microprocessor. And as of 2019, the largest transistor count in a microprocessor is about 39.54 billion MOSFETs, all packed into one chip. That's insane. So 39.5 billion or million. I think it's billion, but it might be million MOSFETs packed into one chip. And then we talked a little bit about operational amplifiers, and doing some research on amplifiers. They have about 20 transistors in the standard 741 package, but there's a lot of different types. In the standard amount of transistors is about 20 or so. So that is my review of chapter 1 of this thing. I moved on to chapter 2 this week, and it's the number system, converting from decimal to different base systems, binary, hexadecimal, and things like that. So I am currently working through this chapter 2, and I will be, giving a summary of that in the next video, talking about that. Like I said, I don't want to show too much of the copyrighted data, but I plan on having some of my own notes to show on the screen, working through the problems and things like that, to do a review of chapter 2. But again, check out the YouTube channel, Digital Logic and Programming. It's fantastic if you want to learn like basic electronics. Also, logic circuits. I'm a huge fan of logic design. I like how logic circuits work. I like FPGAs. I like old logic chips from the 60s and 70s, doing projects with them, and this has been very helpful on doing that and actually learning more than I had known before. So that's going to do it for this, guys. That was my review of the chapter 1. You can check the links out on social media. You can visit me on Patreon if you so choose. But that's it. Thank you so much, and I hope you have a fantastic day.